to open it for a deeper discussion, something we couldn't have done by having a larger forum. So thank you all for joining us, and Roy, please.
Thanks, Amir, for the introduction. Let me just go ahead and share my screen. Okay. Hi, everyone. My name is Roy, or E, if you speak Hebrew. I am the training platform team lead here at Brodmann17. And Brodmann17, as you know, offers a software-only deep learning perception solution for ADAS and automated driving. For that purpose, we have developed our own unique automotive-oriented machine learning training platform. But why? When I started working here, I started as the computer vision researcher, part of the team. And we found out as time passed that we spend more and more time on mundane tasks and errors. And this really hurt our research. It hurt our productivity and our time to market. They all suffered for it. So we started looking around for solutions, available solutions that would help us conduct our research and make our products the best they can be. And we came to the conclusion that our needs as an automotive deep learning software supplier were unmet by any of the available products. So today I'd like to talk to you about building and managing machine learning software. Now we chose this small forum, as Amir mentioned, only with selected clients for the webinar in order to allow for questions and discussion. So feel free to stop me at any time and ask a question. Or if my accent is not clear, please raise your hand. Also, bear in mind that having started as a researcher here, as a deep learning researcher, I have in-depth knowledge of how our users are using our system. So I can answer any of these questions as well, if you have them. Now, since I'm going to be sharing my screen and most of you have your videos turned off, I won't be able to see your faces. So if you don't mind, I'm just going to go ahead and assume you're all continuously nodding in enthusiasm, with big smiles on your faces, and that's how I'll go. Agreed? Okay, I hope you agree. So what I'm going to cover in this short time we have will hopefully fill you in on what I believe are the most important key points in and our platform in particular. I'll start with a general overview of what training models entails from start to finish. I'll detail the important, often overlooked factors that are required for an effective machine learning platform. And we'll see the advantages of our automotive-oriented platform over generic machine learning platforms. We will talk a bit about hardware, specifically automotive-grade SoCs, and the challenges associated with them. And finally, I'll touch upon what lies in store in the near future and how some aspects are already integrated into our platform. So let's start with describing broadly what are the steps one goes through in order to end up with a hardware-compliant piece of deep learning-based software. So you start with your data, right? Be it images, videos, radar, etc. Let's say for the moment that your data consists of images. They have all been annotated in some way and are ready to be digested. Training your model consists of selecting an architecture, setting up a virtual machine with enough resources, and feeding the images again and again to the model, each time correcting its mistakes. This is a process I'm sure you're all familiar with. So you then have a model. How good is it at what it should do? Say we are detecting pedestrians. Does it detect them all? Which one is it having difficulties with? Maybe it fails with smaller, more distant objects. Maybe occlusions fall out of the track. Is it better than the baseline? By how much? So maybe the distance estimation is off, right, at the end of the track, and the collision detection fails as a result. These questions are all part of the so-called analyze block. You then go back to your drawing board, come up with a few ideas about how to make it better. augment the images in a novel way, or change some layers in your model, implement a method you read in some paper, etc. And then you train your models, you analyze them again, you adapt again, rinse and repeat. Finally, after this iterative process, you deploy your model to the hardware and you measure the results, right? Well, not so easy. I really hope you were a bit uneasy when I describe the process, because it's not so clear-cut. It is time-consuming and it's expensive. First, I wrote data, but it is actually an entire world in and of itself. We explore the data. We want to know what is the nature of it. Are the videos similar to each other? Do we have enough variety? Do we have fisheye input? Maybe some of the images are blurry, some of the videos are too dark. Is the driver standing in a traffic jam for 10 minutes, giving us hundreds of gigabytes of almost useless input? So naturally, the quality of the data is as important as, if not more so, than the quantity of it. We refine the data. We discard the redundancy. We gather more informative resources. We implement novel augmentations to account for what we don't have. We use simulated data. We annotate the data using machine annotation or human annotation, prioritizing it since it's an expensive and slow process. Then we go back and we do it again. It's a very interesting aspect of the job. Furthermore, if we go through all the motions and deploy the model to the hardware at the end of it, we get a suboptimal solution. We want the hardware to be the centerpiece of our process. And of course, all the steps are intertwined with researchers training, analyzing, adapting, deploying, refining the data again and again at various stages of development. And this is why we need a robust platform to help us achieve the best results. In the previous slide, I described a single process, so-called, of training a model. To make things more complicated, and this is the general challenge people face, many researchers work on many projects, and each project has many research directions. So this can get messy very fast. A good platform should help accomplish as much as possible, as efficiently as possible, while allowing for everyone to work together as a team. So I hope that having all that in mind, you'll see why these next points are very instrumental in building a potent training platform. The first point is dependability. It must manage the infrastructure with little to no manual oversight. We're talking about setting up servers, tearing them down when finished, restarting when things go wrong, network issues, logging. These are all tasks that, if they have to do themselves, they take away from the time the researchers spend on what is important. The platform must allow for experiment reproducibility. If you train a specific model on specific data with specific parameters once, you want to make sure that doing it again produces the exact same results. The hardware, the environment used, the tests, they should all be deterministic. Otherwise, you cannot be sure of the quality of the product you're releasing to the customer. When it does reproduce reliably, then your conclusions are sure to be based on the research alone, and not on factors that are outside of your control, or even worse, factors that you are unaware of. And another point towards making your platform dependable is that you can count on it to tell you when something is wrong. Be it your code misbehaving, or maybe the server is not starting time, your team is closing in on the monthly budget, your results are a lot worse after that code update, your resources are not utilized efficiently, etc. If your system has all these attributes, then you can sleep. At least I can sleep easy at night. Now, our platform boasts complete decoupling of researcher and infrastructure. The researcher can fire and forget, knowing that issues will be brought up if they arise. We have monitoring, we have alerting, and cost management, which is important. And also, most fault tolerance happens behind the scenes without even troubling the user. The next point is flexibility. If you are trying to beat the state of the art in your field, then you must explore many, many directions. And if you're working on different projects, each with its own challenges, then you must support all kinds of procedures. And you must keep yourself and your code updated with the latest and hottest in the field. With our platform, researchers manage their code base and are free to update it as they see fit. They choose their model configuration. They select the most appropriate data and data augmentation techniques. Plus, they are free to utilize any number of hardware platforms and resources. What you see here is an example of a model that is used to detect objects in images. The model's configuration with its hundreds of parameters is fully controlled by the researcher. But there are also checks and balances in place to make sure she is aware of any unorthodox method that she put in place. Our next factor is performance analysis. We will be driving blind, pun intended, if we can't look deeply into our models and find their strengths and their weaknesses. In fact, a large part of the researcher's job is to be able to find solutions to various ailments that pop up with their models. Quantitative, that means that you want to see the accuracy improve over time. The validation accuracy versus the train accuracy, are they close? Is your model performing better on one metric than the other? Is it better than the baseline? Did it succeed in throwing the forward collision warnings earlier than the baseline? There is a lot that we can deduce from these numbers. In addition, we are fortunate to be working with visual data. So we have the privilege of seeing with our own eyes how our models perform qualitatively. We want the platform to offer us convenient ways to see our model's performance, both on images and videos, selected flexibly on demand. Also, training deep learning models takes time. It's very helpful to be able to monitor these metrics during the process, and not only at the end of it. So let me dive in and show you some examples from our platform. What you see here is a plot of accuracy over time. Actually, let me just go right in here. So this is an interactive view of our platform. So I said that the x-axis represents time, training time, and the y-axis represents the value of the metric that I've chosen here. Let's focus on these two lines here, the brighter orange and the darker orange. So the brighter orange line represents the train accuracy of the model over time, and the darker orange line represents the validation accuracy. And you can see that the train accuracy is higher than the validation accuracy, right? Which is an expected and desired phenomenon. And even here, even though they seem to converge, they don't really converge. So by looking at these numbers over time, I can rest assured that everything is working fine. It doesn't always look like this. Sometimes there are problems, obviously. Looking at the other model, this is a different model. I'll zoom in here. So again, you see the training accuracy against the validation accuracy. And you see, again, this is the same phenomenon that the train accuracy is higher than the validation accuracy. And you can see that it behaves differently. It has these jumps at 30 and 60 because of the way the model was specified, the learning rate schedule. So you can see that I can easily compare the model within itself, some metrics against the other training versus validation, and I can compare two or more models, one against the other. So going back to the presentation, let's look at some more things we have in our toolbox. Obviously, we have access to the raw numeric numbers that make up what I've shown you in the graphs I've shown you, and we can massage them and get a lot of insights from them in their numeric form. super important. And of course, I've talked about the qualitative inspection of your results. So in this case, I'm showing still images from a front-facing pedestrian detection model, working with monochromatic data. And in these galleries, we can see the correct detections. We can see the false alarms, like fire hoses marked as small people, and we can see the misses. For example, is it having difficulties specifically with smaller, more distant pedestrians? Maybe it's less observant of occluded pedestrians, for which only a part of the body is visible. We can also compare the detections of one model against another. So as I've mentioned, looking at the results with our own eyes is priceless. So going back to our factors to consider for efficient platforms, of course, no deep learning when needed, selecting it, digesting it. It is a crucial part of any machine learning endeavor. So what do I mean by selecting data? Good data from bad data. I mentioned it earlier, but I want to give you some examples. Say I have 10,000 video clips from dashboard cameras, but a lot of the videos are of deserted highways, or maybe being stuck in a traffic jam, tailing one specific car for a while. If I use only these clips as my model's training set, I can assure you it will not be very good at recognizing vehicles. So it's clear that diverse data is needed. We would benefit from a system that shows us which data is most diverse. Also, which data is okay to annotate with a machine, and which data is best to send to a human annotator for data cleansing and improvement, which is an expensive process. Excuse me. In addition, we must make sure that the training data does not get mixed up in the validation or test data. And this is best done as automatic rules because human errors are abound. Here, you can see a screenshot of statistics of weather conditions in some 5,000 videos, also locations and time of day. And tools like this enable us to know, do we have enough pedestrians walking in the rain in rural environments wearing black clothes? Are we missing road markings next to construction sites? The more we know, the better our product will be. And there's another factor that I haven't talked about yet, but is equally important, and that is user-friendliness. Even though we have very talented people working with us, we still need to make sure that they can utilize all the goods we throw their way with as little effort as possible. Okay, so let's talk about other available products, what they offer and what they lack. There are a lot of available products out there that take care of the training process. Usually they offer experiment management and/or infrastructure management. Experiment management, as I've mentioned, is the process of saving the configurations of each experiment, sorting, filtering them, and managing their states, right? Starting them, stopping them, resuming them, all those fun stuff. Infrastructure management, that's setting up your servers to train the models, monitoring the resources, serving the models. And some of these products out there, they do an exceptional job at this. However, the automotive industry's challenges have two distinct additional requirements. The first is the hardware. The platform must support different SoCs, each with its own advantages and disadvantages. And I'll expand on this in the next slide. The second is that detecting objects on the road is not enough. So let's take forward collision warning software, for instance. In addition to the object detection, there are also object tracking, lane detection, and lane tracking. And on top of these, we run models that estimate distance to target and which object, which vehicle in this instance is the most likely to be collided with. Then we have models that calculate time to collision. And finally, we have forward collision warning or auto braking models. Components run on dedicated cores in the hardware or must share cores, increasing the system's complexity. And each of these models has accuracy, latency trade-offs, and changes to each affect all the others. And now there's also the dimension of time. It's important to, that the collision warning will be dispatched at exactly the right moment. So it's imperative to have all these pieces of the puzzle trained, analyzed, and improved together. And this is supported in our platform, but it is not part of the general use cases that the generic platforms cater to. So let's talk a bit more about hardware. Hardware is arguably Brodmann17's most important factor. Hardware constraints are notoriously hard to take into account when developing new machine learning software. To meet this challenge, we integrate the hardware constraints during the train, adapt, analyze cycle I discussed at the beginning. This is achieved with two complementing methods. Wherever possible, seamless integration of the actual edge hardware is used within the same platform. However, in order to avoid the need for a huge SoC farm, we designed various accurate simulations and estimations. And these are employed when using parallel processing at scale. This allows our researchers full flexibility with different SoCs. They can both take into account the target hardware while developing their product and test it hands-on at various stages of the process. So let me give you an example. In the screenshot I put here, you can see the results of a sophisticated method to select the best parameters for a specific model on a specific hardware for a specific product. The x-axis represents the latency or runtime of the model, so the lower the better, and the accuracy, of which many different metrics are available and chosen depending on the use case. So this was produced automatically using hundreds of servers behind the scene, all of them simulating the exact environment of the target hardware and reporting the results back to the platform. And I think it deserves a bit more attention, so let me just jump right in here again. So this is the same screenshot I took. So as I've mentioned, the x-axis here that I've chosen, and it's obviously flexible, is the latency, and the y-axis is the accuracy. So we want the models to be on the top left. And you can already see that some values, some sets of parameters produce models that are better than others. For instance, let me switch over, okay. For instance, this model here that produced this point is better than this one because it has the same latency, same speed, but it's much more accurate. Also, if I'm taking these 2 points here, so this point is better than this one, hands down, because it has the same accuracy, but it's faster, right? So you can already see that some points here can be discarded without an afterthought. And all the points that are on this line here, this so-called Pareto line, offer the best trade-off between accuracy and latency, right? So each point here is dispatched on a separate server, run automatically with its own set of parameters, reports the results, simulates the environment, the hardware environment, specific for the target hardware for the product, and then reports the results back. And then the best sets of parameters are chosen and dispatched to the hardware itself to be run there, and then we complete the cycle. So going back to my presentation, I think this blob of points does not do justice to what it actually means. The process of exporting a model to the hardware involves a lot of choices, a lot of optimizations. And these are specific per model, per hardware, per product requirements. Even though I've not really explained in detail what's going on here, you can imagine how infeasible it is to do everything, think of everything, and especially keep track of everything manually. And you can see why everyone started liking me more when all this became available to them. And this process is only possible with both of the points I mentioned earlier. Shrewdly simulating the hardware environment and connecting the hardware itself to our platform. And note that utilizing our various tools produce much faster and more accurate models than the vanilla method of training models and then porting them to the hardware at the end. Now, it is widely accepted in both academia and the industry that the next step towards better performance is in automating many of the manual steps the researchers are utilizing. All the points I mentioned thus far are automation of the infrastructure, of the data selection, of monitoring the training, and so forth. And here we talk about the next step, automating the process of coming up with the best model for the task. Under usual circumstances, there are hundreds of billions of possible models to choose from, and it would be best if the best model could be found automatically. Now, there is a lot of know-how in the industry, but often we do not have all the answers in advance. Let me take a moment to paint a clear picture. So imagine Joe. Joe is a researcher that is tasked with coming up with the best blind spot detection model. After some time, he has a model that performs pretty well, but it fails often with motorcycles. He tries to tweak the model in a few ways and starts training new models. A day or two pass, and he sees that one of these ideas produces a better model, but not good enough yet. So he tries some more ideas. Another 2 days pass, and now he finds that there is a problem only when the sun hits in some specific angle. He needs more data. So he collects new data and adds it to the training. Another day passes, and so forth. So it is unquestionable that he will train a very good model at the end of this process, if he knows what he's doing. But it takes time, and it takes money. It would have been preferable if Joe could put all his knowledge into an automatic process that would do all of this on its own 24/7 and produce an even better model at the end. It would help performance, it would cut the time to market, and allow for each researcher to be more productive. Now, this has been a very hot research area for the past 2-3 years and has been dubbed neural architecture search, or more broadly, AutoML, for automatic machine learning. And we here at Brodmann17 are constantly up to date with the latest state-of-the-art methods coming out of academia or the tech leaders in the industry. We constantly integrate new AutoML and NAS methods and come up with some of our own. So the challenge here is to take it out of the sterile academic environment and into our real-world constraint-heavy applications. It's also important to integrate these methods into the development pipeline as more tools at the disposal of our researchers in tackling new challenges that arise. Some of the state-of-the-art methods we use that you can see here are genetic algorithms, differentiable architecture search, and hyperband, among other proprietary methods that I do not cover here. So let me zoom in on this graph here just to illustrate what I mean. This is an output of a genetic algorithm that we conducted. Each node or leaf in this tree, so each ellipse, is a distinct model. And the number inside, which I don't know if you can see clearly, and the color represent the accuracy of the model. So the higher the better, and the darker the better. The root node here is the best model the researcher had at the beginning of this process. And then this process started automatically with mutations, slight changes to the models being done on the best model at each time. So the arrows signify a mutation, okay? And each model is trained on its own server, and this process goes on automatically. And at the end, the researcher has two things. First, she gets a model that is better than the one she had before. And second, not less important, is that she gets a lot of insights available to her from the process. So which mutations work, what parameters are important, etc. She can then take this output model and continue with her research, being it manual or additional automatic steps. And putting it all together, we get a very flexible, productive, and efficient platform that our researchers use in the day-to-day to come up with our state-of-the-art products. In this video, which I hope you can see smoothly via Zoom, depending on the network latency here, you can see front-facing 3D vehicle detection with distance estimation. It runs in real time on 𝗟𝗿𝗟𝗟𝗪's CV22. Summarizing what we've talked about, we discussed the challenges facing machine learning platforms, including the data pipeline and the unique hardware constraints. We discussed the future of machine learning platforms in regards to automation, including some of these advanced capabilities that are already built into the platform. And we've outlined the advantages of our platform, which is geared specifically towards the automotive industry. Support for the hardware needs and constraints is integrated into the platform, and the various software components that are combined together to make up the holistic software solutions that are required. Finally, being developed in-house means it's very flexible in helping us do what we do best. So in other words, we developed this comprehensive platform to optimize the entire neural network training process. The data selection, the parameter tuning, the neural network architecture search, and deployment to the target embedded processors. And by optimizing the process as a whole, as opposed to optimizing each stage separately, a much better neural network can be achieved to meet the customer's given requirements. And that's it. I'd like to take some questions if you have them.
Roy, hi, this is Tony speaking. Tony for saying. Quick question. So you say, it's automotive focused. Is that purely because of the SoCs that you've integrated on the platform, or for some other reason? And how adaptable is this to maybe to other industries?
So let me just grab my headphones here to hear you better. 1 second.
Shall I repeat my question?
Yeah.
Yes. So my question is, you mentioned, and I've heard several times from you guys, that it's very much tailored for the automotive industry, and it's an automotive-focused platform. Mm-hmm. Is that purely because the SoCs you've integrated and simulated in your platform are the automotive SoCs, and you could, simulate and integrate other SoCs that are not automotive? Yeah, how easily adaptable is this to other verticals, other industries?
So yes and no. I have two answers. So first of all, yes, we work with automotive-grade SoCs, and we have accumulated knowledge in how to connect them to the network and how our models should integrate with them. But that's not all. Also, the components of the whole software, as I've mentioned, are geared specifically towards the automotive needs. So because this platform is being used continuously during our research, it has been evolving with time to allow for easier productivity, easier production of software that caters to these needs. So you have the SoCs that we use and the holistic software solution. In answer to your second question, how easily adaptable it is to other hardware, the answer is it's quite easy. So obviously we haven't started out with all the hardware we utilize currently, and we've gathered a lot of know-how about what are the easiest, fastest, best steps to take in order to use different hardware.
Yeah, I just want to emphasize that I think it is very important for us as a distinction, and Roy also went over it in this presentation, that you have this general machine learning you with very generic tools. And that's basically in order for them to support many different types of customers. And also in their work, I think the main component which is missing are algorithmic workflows. I think that anyone who has tried to do some applied machine learning, not as a hobby, but you actually would like to get into a production grade product, then you would have to do many different steps and combining many different algorithms in the steps in order to achieve your final goal, perhaps adding different components. For that, you need to define specific workflows. In our use cases, we have defined automotive development workflows as we understand for the different products we are developing and the different customers we are supporting. So this is very important and very helpful because it's not a standalone model that you have to train, whether it's for detection or segmentation, but you would like to actually develop the entire pipeline and running it on the hardware. That is, we think, critical, and this is actually missing from any platform out there that we are aware of. And of course, it is adaptable to any other use case, but of course, from our daily work and our main focus, we have adapted to automotive and our use cases. And we also hear a lot from the different companies that many of the products out there. Perhaps I'll raise a question for the audience. But what do you think about existing I don't know, tools? Like, did you have to go ahead and develop your own tools in order to support your research and development, or have you used a third-party tool and did customization on top, or what do you think about it?
I think the silence means they have lots of woes and troubles with their existing platforms, similar to what we had.
Yeah, this is 𝗟𝗲𝗟𝗟𝗪 here from Continental. This is really one of our challenges, and you know that very well. I do have a question about what you mentioned earlier. Mm-hmm. You mentioned earlier that simulation, or you didn't call it simulation, but you said it's 24/7 that the data is trained. Mm-hmm. The percentage of training, automatic training, and I would say handmade training, what's the repetition of percentage, perhaps, if you can give it, if you know?
Well, it depends on what you mean by automatic and what you mean by manual, because as I've outlined, a lot of the things that are so-called manual also have automation behind the scenes. Mm-hmm. So, for example, if you let the platform train a model, and you tell it also run error analysis and benchmarks every so often in this way and in this way and in that way. And then you come back tomorrow and you have the model also trained and all the benchmarks are ready and the metrics are ready and everything is already ready, right? And all the benchmarks are running on different servers and everything. So this is also automation, but you did start the experiment manually.
Yeah, this automation, would it help you then also for false positive suppression? The false positive is already at the end of the chain, of course. If we do have a false positive, and then it starts the retraining, the revalidation, what is very painful, time consuming, mm-hmm. and we cannot be sure from a statistical approach or from a classical approach, we cannot be sure that the changes we made will not change other things we don't want to be changed. Yeah. So have you already thought about that?
This is like the first thing you think about is what you raised is a valid concern, and this is why you must set the metrics that you want to optimize in advance, and you have to be really rigorous about it. To make sure that no mistakes like the one you mentioned can happen. So obviously, if your model, your new model, say, outperforms the baseline in one metric, which is important, but falls short on a different metric, then you can't really know which one is better. Am I correct in addressing the issue you're raising?
Yep.
So, okay, so it's really important to have your product requirements in mind and to know exactly what you're trying to achieve. And we discard models that are better in one aspect, but not in all aspects all the time. Also, I've touched upon it in the accuracy latency trade-off that I've discussed. You have some models that are obviously inferior to others, but you have a lot of models that are on this trade-off line that you have to select according to your product requirements, right? So you may have a different model and you wouldn't know which one to choose until you know exactly what the product requires.
I think specifically, Christian, correct me if I'm wrong. You're talking about you have one version of the model, and then you would like to keep the same performance, but perhaps improve it in one vertical without hurting the rest, like moving forward in all fronts, right? So this is
this is at the end, just before start of production. What is our day-to-day business? We have false positive, and we have to eliminate false positive without damaging the overall performance.
Yeah. So this is exactly the pipeline 𝗺𝗍 has shown in the beginning. So basically, no matter at what point of the development you're starting, but you would need at some point add new data, or perhaps re-annotate data, or introduce more data of a specific kind, and then of course retrain, do the analysis, and make sure you're actually moving forward. So this is also one of the KPIs we can define, and this is a lot of and this is very frequent in our development. So we finish a version, we send it to the customer, of course, after we do our rigorous testing, and then he has some examples on which we still need to improve. So the digestion and retraining and making sure that everything that worked before works and still getting additional improving, this is done using the platform. Of course, it requires, it's not everything, of course, is automated. We provide a lot of the tools for the researchers to do the fast iteration. So for instance, if we ingest new data and we require it to perhaps focus on part of the, on specifically perhaps oversample or overweight some of the examples, retrain, running on the hardware, get the benchmark, making sure everything, all the tests we've defined have passed, and also the additional ones. So these are doing these iterations requires the researchers perhaps a single click instead of 7 or 8 different steps. So this is, I think, the main benefits, and all the automation algorithms and the search are part of the tools that goes behind the scenes. Some cases they work better, in some cases other tools work better, but we are trying to reduce the interaction with the researcher to make his work more efficient. I don't think full automation is currently our goal, but rather to improve the iteration, improve the interaction, because the researchers at the end, if you need to develop a new algorithm, perhaps a supporting algorithm, or change something dramatically, this will come from a human intervention, but we'll provide them a lot of the tools to enlighten him, to give him strong insights, and to eliminate a lot of the tedious work in order for him to do that. If he has come up with a new way, with the new meta algorithms and so on, we will incorporate it into the system, allow it to perhaps expand a bit, but this is the main purpose there. And we see the use case you're describing, we see it all the time. This is, of course, a lot of the work we're doing, a lot of the work cycle, and this is also one of the main benefits of developing your own platform. because this is a routine work that repeats. Yeah.
Okay, thank you.
Thank you for the question. Do we have any more questions? Okay, in that case, I'd like to thank you very much for taking the time and listening to my webinar presentation. I'm sure you're already familiar with most of the stuff I said. I hope I managed to enlighten you on some of our internal workings, motivations, and challenges. And by all means, if you think of another question that you have regarding this material, please feel free to contact me through any of your contacts in Brodmann17. They have my mail.
Thank you.
Thank you, Roy.
Thank you all.
Thank you all.
Thank you very much.
Bye bye.
Thank you very much. Bye-bye. Bye-bye. Bye-bye.
Bye.